Hello everyone. Joint PhD program between University of Queensland and IIT Delhi, and I'm the TA for this course, Introduction to Lasers and Laser Systems. So in today's class, basically for this week, the professor has discussed interference, anti-reflection coating, diffraction, scattering, and polarization. So I'll briefly discuss all this concept, then I'll discuss some questions for the quiz. So let's just start. So basically, what is the interference? Basically, if you have two slits and there is one source, so the wavefronts for each slit like interfere with each other, and they form a pattern on the screen. That is the phenomena is what is called interference. And this phenomena also prove the wave theory of light. When two or more disturbances arrive at a sorry at a point in space simultaneously, the resultant disturbance and that point according to the principle of superposition is given by the vector sum of the disturbance which are assumed to be small. And so if psi1 and psi2 are the wave function for the disturbance, then the superposition of them is can be given by psi1 plus psi2, because both the differential wave equation is like also have the solution psi1 plus psi2. This is the normal way. But when monochromatic waves of sources proceed almost in the same direction, and superpose same same or in the opposite phase, then the intensity of light at that point will be maximum or minimum according to the waves meet the point in the phase or out of phase. This phenomenon is called interference. So basically, when two disturbances arrive at a point, so that at that point the two disturbances will meet at the as a principle of superposition. So if we go to the quantum mechanics, we have a wave equation. Not only quantum mechanics, we basically have a wave equation like this. And in quantum mechanics also the waves are denoted by psi1 and psi2. But however, consequence of principle of superposition is that when two beams of light intersect, the propagation of each beam is completely unaffected by the presence of the other. But when they are crossing, then the super, like, we will get maxima or minima. And if they are monochromatic waves, it's depend on the if they are superposing at the same phase or the opposite phase. And this special phenomena that their in intensity can be maximized or minimized or in between, uh, because of when they are meeting, either they are of same phase or opposite phase, is called interference. Here, for the presence of one slit, the wavefront of other slits get affected. That is the basic thing of interference. So let me let this thing. So, So as I was discussing that when there's a slopes and two similar sleeves are open in front of the source and it has to be parallel. And the each of front have like crest. This is crest, this is crest, and this is trough. So these 2 points will act as secondary source of the wavefront. Let us so here it's not getting aligned, but at the where this distance is the same from both this point, we'll get a bright spot. And when all the throbs are getting like this point, and here that will get all the throbs are matched and in the line, we will get dark spot. So I say that if the waves are superposing at phase or out of phase, so we can also say the definition in terms of path difference. When the light beams meet at zero or integral path difference, we will see the bright spot, and when they meet the path difference of lambda by 2, 3 lambda by 2, 5 lambda by 2, we'll get dark spot. But the brightest, like after this is the brightest spot, after you get dark spot, then another bright spot. But the most brightest spot is this. And port on where path difference of two waves are zero. And we will get the intensity as a function of path difference like this. So for path difference 2n lambda by 2 will get bright spot and path difference 2n plus 1 lambda by 2 get dark spot. So here one thing is that zero path difference will get a bright spot at lambda by 2, dark spot at lambda, again zero path difference. At lambda it's basically again act as a zero path difference, but it will not be the brightest spot. Brightest spot will be here. Now, by using this phenomena, anti-reflection coating basically works. You can draw intensity as a function of path difference also. Like not path difference, the phase. Delta phase. And the maximum intensity we get that if the disturbance is have amplitude A1 and another disturbance have amplitude of A2 omega t minus kx2, yeah, it is k because it has circumstances y2 disturbance and their amplitude are A1, A2, then The disturbance varies on the screen. A1 square plus A2 square plus 2A1 A2 cos delta. So delta is basically the path difference x2 minus x1. Like x2 minus x1 is the path difference and delta is phase difference. So we are calculating disturbance at a distance p, that is x2, x1. So the y1 is a disturbance due to first slit at p, and y2 is the disturbance due to the second slit at p. So intensity I is that if A1 is equal to A2, A square plus 2A square cos delta. So 2A square 1 plus cos delta. And now when the delta changes, we get maxima or minima. Going on to complex disturbance. Slit and y2 is the complex disturbance at P. Due to second slit. So when x2 minus x1 is 0, then delta is also 0. Then we get maximum intensity, which is A1 plus A2 whole square. And if A1 is equal to A2, so that is V square. And when delta is equal to 90 degree, 270 degree, and so on and so forth, then I is basically 2 square. When delta is equal to 180 degree, 7 degree, then not 720, it is 540 degree. Then I is basically 0. So 90 degree is like at this position, half of the maximum intensity at this position. So we get the maximum, then half of the maximum, then dark, then again half of the maximum, then bright. That is the concept. And the main question is the light energy destroyed by interference? it is no. The answer is basically no. We can show that by this average calculation, that I average is basically 0 to 2 pi I d delta by 0 to 2 pi d delta. So I we know is basically a1 square a2 square plus 2a1 a2 cos of delta. And if we do the differentiation, so this is basically 2 pi and this is 0 to 2 pi a1 square plus a2 square plus 2a1 a2 cos of delta. We get the answer a1 square plus a2 square. This is sum of intensities of intensities of individual waves. So we can say that the light energy is not destroyed by interference. So we need to remember this intensity equation denotes any intensity at any point at screen. Depending upon on the delta, I value varies on the screen. But this expression can give the intensity at any point at the screen there, be it P here or here or here at somewhere else. Here the P is maximum, which is 4 square, because delta is 0 basically. And the shape of the interference fringes also depend, like for cylindrical interference, for like spherical wavefronts will get different shape. If the wavefront is cylindrical, we get different shape and so on and so forth. We can discuss that later if the situation arises in this course. So there is also condition for observable interference pattern. Like we for the interference to be observable, the light must be coherent. They should have the same frequency, and the original source must be monochromatic, and so on and so forth. But here we are not discussing the normal interference thing. We are discussing interference because of the interference we can because of this interference phenomena we can use this interference phenomena to enhance the laser working. That is what. So all the nitty-gritty of interference is not in the scope of this uh, course. So we will discuss anti-reflection coating now. So basically, this is glass. This is the anti-reflection coating, and this is air. Because of the reflection at that surface, some of the light is lost due to reflection at lens surface. Although the loss is very small for a single surface, in a multi-lens system or multi-layer system, the loss is significant. So we need to reduce this loss. So basically, to eliminate the loss is to use a thin film. So the two consecutive reflected rays, like one reflected ray from this surface and another reflected ray after two reflection come from ray. So these two cancel out each other. That's the logic of anti-reflection coating. Under this condition, the reflected waves undergo basically a complete destructive interference. Q R and Q1 R1. So QR and Q1 R1 undergo a completely destructive interference. So that's how anti-reflection coating does work. Sorry for this inconvenience. The PowerPoint is not working. So I'll PowerPoint like it's stopped video. So the work could not be saved. I'll write those after the class and upload them. But let us start with this anti-reflection coating. according to electromagnetic theory of light, the reflectivity are at the boundary between two media of refractive index indices N1 and N2 for normal incidence is given by R N2 minus N1 by N2 plus N1 whole square. So to cancel QR and Q1R1 completely, their amplitude of the waves should be the same. So here the air has the reflective index NO, that is NC, that is for reflective index of coating, and this is NG. So QR is being reflected from air and glass. So coating or glass, not air and glass, coating and glass. So NC minus NO by NC plus NO whole square is equal to should be Q1R1, which has reflective reflection like contribution from this surface also, that is coating and glass. So to completely destroy the reflection, QR and Q1R1 needs to be of equal amplitude. We can say the reflection should be of the same. So reflectivity is same. So from this equation, we get the reflective index of anti-reflection coating glass is N. And D, even though I have drawn this like oblique incidence, the equation I am writing for normal incidence and some right from this. So QR, Q1R1, they happen to like this. So that is lambda by 4 NC. So this path difference to NCD must be equal to half of 1% from this equation to NCD, like this light is crossing double time. That is why. So d by lambda by 2, get the thickness should be of lambda by 4 NC. So the interference of the light causes Newton's ring and thin film reflection problems, multiple beam interference, and all those things. But here we are discussing the interference problem as part of the laser system. So, as Professor has said, to get the transition window of laser, the laser medium can have the structure like this, where the active medium has anti-reflection coating, glass and anti-reflection coating at both sides. And the cavity forming boundary can have this structure. And we need partially reflecting surface, so one side. So this side need PR, partially reflecting coating, glass and anti-reflection coating. That will enable us to basically couple the laser beam greatly. Basically, this arrangement will ensure the light beam goes through the active media multiple of times. So now I'm gonna discuss some basic interference problem. So I have already discussed earlier that intensity at any point at the screen of the interference can be written as A1 square plus A2 square plus 2A1 A2 cos of delta. Here A1 is the maximum, not maximum, is the amplitude of the disturbance of wave at point P on the screen. So this point P can be anywhere on the screen, and the main thing is due to slit 1. I'm writing upper slit as a slit 1 and this is slit 2. So the source. The path difference between the two waves at point P is x1 minus x2. And A2 is amplitude of the wave at P on the screen due to slit 2. So the intensity at P due to interference is A1 square plus A2 square 2A1 to cos delta. Up and down the screen, delta varies. So the intensity. I max is when cos delta is 1 and I minimum is when cos delta is minus 1. So when A1 is equal to A2, I minimum 0 and I max is 4 square. But if A1 is not equal to A2, we would get A1 minus A2 whole square as I mean, and I max is A1 plus A2 whole square. So you can see that if the amplitude of the wave is not equal, we are not getting complete darkness. One will be the bright spot, one will be the light spot, but that would not be the dark spot. For making the dark spot, we need A1 is equal to A2, which generally happens if the slits are of the same size and at the same distance. That is basically generally happens because if this S1 and S2 reside on the wave front of the source, is bound to be happening 1 1. A1 is equal to A2. So the question is, in a Lloyd's mirror experiment, calculate the ratio of the intensities at the interference maxima and minima if the mirror reflects only 75%, 95% of the light incident upon it. So we don't need to know what is Lloyd
Ma'am,
experiment. Hello.
ma'am, can you? Yes, ma'am. Can you please go to the previous one?
Okay. Here.
Yeah, done.
Okay.
No, 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 no. Done.
This one.
Yeah, yeah, yeah.
Yeah. What is your question?
No, no, no. Actually, I just want to see the question. I didn't write.
Okay, you don't need to write every question now. I am uploading these things in the Google Drive. So after this class, I'll upload these things. So I'm
No, ma'am. Actually, I was trying to solve the question. So
okay,
that's
okay, okay,
it.
okay. Then do that, do that. When you are done, you can tell me. I can go to the next slide. Okay.
And I'm done, ma'am.
Okay, okay.
You can go to the
So
next.
okay. So basically, what I was telling that we don't need to know to solve this question what is Lorentz mirror experiment. Either it is a division of wavefront interference or division of amplitude interference. Like I know most of you know that, but it's not necessary to solve this question because this question basically solves from the Imax and Imean equation. So here the answer is reflectivity is 75%. So that is 7500. So that is 3 by 4. Okay. So amplitude reflection coefficient is basically root of R. So that is root 3 by 2. And A1 is the amplitude of direct beam. Then A2 will be root 3 by 2 A1 because of the reflectivity. So I max by I mean would be A1 plus A2 whole square by A1 minus A2 whole square. That can be written as A1 plus R whole square by 1 minus R whole square. Two is equal to root 3 by 2 A1, or you can divide this thing. So A2 by A1 is basically R. So we get this thing. So 1 plus root 3 by 2 whole square, 1 minus root 3 by 2 whole square. That is 194. So I max is basically 194 times of I minimum. Even though I min is not completely zero, we can see the stark difference between the maximum bright spot and the minimum spot. And I'm sorry that I said that you don't need to know the Lloyd experiment method. Like you should have a way like idea that in Lloyd experiment, what happens that the interference has is between the so this is the actual beam. So this is the Lloyd mirror. So interference causes between the actual beam and the reflected beam. And this area we get the interference fringe. So this idea you need to get because otherwise you will not get the relation between A1 and A2. So let me draw the Lloyd's single mirror experiment properly. So basically this is Lloyd's mirror. This is the source. So light comes from like this. Light is going like this also. And the reflected light goes like this. So in this area, so this whole red area is the light coming from the source, and this blue area is the reflected light. So in this area, the interference happen between F and E. Reflected beam, it seems like it's coming from a source called S2, and this S1 and S2 are like coherent, acts as a coherent source. Question number 2. Find the thickness and refractive index of an anti-reflection coating necessary for a glass lens that is refractive index is equal to 1.5 in air at vacuum wavelength 590 nanometer. So first we need to calculate the refractive index of that coating, that is NC is NO in G. So NO here it is not mentioned what it is. So we oh no, it's mentioned that necessary for glass lens in the air. So it is air one, and glass lenses refractive index is given 1.5. So that is root 1.5, that is 1.225. So we got the refractive index of the coating. And the required thickness is T is lambda by 4. Here you need to understand that when the wavelength of the light changes when it is in air, then and when it like travels into the coating or the glass. So this lambda is basically lambda c, the wavelength of the glass, the wavelength of the light in the coating. So that is lambda c by 4. So lambda c is lambda o by n c, that is in glass. So lambda naught 4 into nc is equal to 590 by 4 into 1.225 nanometer, that is 120.4 nanometer. So this should be the coating of the anti-reflection coating on the glass. You can see that it's in nanometer, or it's basically in micrometer. It is 0.1 micrometer almost. So a 0.1 micrometer anti-reflection coating makes your eyeglasses like you cannot see the anti-reflect. You cannot see the reflection of your glasses when the photograph is taken or other thing. So that is because of anti-reflection coating. So next thing professor has discussed is basically diffraction. And basically what is diffraction? So when a light bends, let me okay. So the diffraction of the light is the process of its bending or spreading when it passes through an aperture or obstacle at this path. Like an obstacle can be like this. The light is passing through like this. This light rays, first of all, light rays are not that discrete. But the idea is that the light ray coming from at the edges of that obstacle are completely blocked. You can see that it can bend like this or like this, depending upon the obstacle size. And this kind of bending happen when light is blocked most the path, but one slit is there. So the light bent like this. But when the obstacle is there, light bent like this, that the shadow of this obstacle is not of that size, but the less of the size. That is because of diffraction. So the diffraction of light is the process of its bending or spreading. This is bending, this is spreading. Out upon passing through an aperture or interacting with an obstacle. So if the size of the aperture of the obstacle far exceeds the wavelength of the light, then this passage will be unhindered by their light presence. So basically, diffraction is not been discussed as elaborately. Let me discuss a few things. said basically diffraction is Fresnel's divided by Fresnel's diffraction and Fraunhofer diffraction. And what is the main difference between Fresnel's diffraction and Fraunhofer diffraction? Is because one is near field and one is like far field. So Fresnel's diffraction is basically the near field diffraction. What is near field? So the near field basically the source and the screen at finite distance. So source and screen at finite distance. So what is the difference between finite distance and not finite distance? Like if the source and screen and how can we place the source and screen at very large distance? So if the light is coming from very large distance, if the source is kept at a very large distance, the light beams are parallel. But if it's coming from a nearby source, like the wavefront, it's like plane wavefront. The parallel is not a good way to say that. That for Fraunhofer, Fraunhofer diffraction, it's far field diffraction. So that means the source and the screen at far. The wavefront here is plane. But for Fresnel's diffraction, the wavefront can be the cylindrical or spherical. And the another difference between this is the Fraunhofer diffraction. To make the wavefront plane, we need convex lenses. So it became distance independent. It is distance independent. And Fresnel's diffraction is distance dependent. And the wavefront is basically cylindrical or spherical. So what does that mean that it is distance dependent? That simply means the Fresnel's diffraction, if you change the distance between the aperture and the screen, the pattern changes drastically. But Fraunhofer diffraction doesn't change like that. So you are not getting a like fixed pattern for Fresnel diffraction, but you can get a like simple slit-like pattern for Fraunhofer diffraction. So I can show you how the pattern varies. Like I will show you in the next class how the pattern varies upon the screen, and when you change the screen and aperture distance in the Fresnel's diffraction, because in my drawing it would not be apparent that is the patterns is being changed, but in Ajay Khatak's book there is a like a picture how they changes and all. And another thing that has been discussed in the class is scattering. So basically, relic scattering, mean scattering, they are all elastic scattering pattern and happen in the nature. So in the relic scattering, the main thing is the particle size are very less than the lambda wavelength. For mean scattering, the wavelength, the particle size is almost equal to or greater than lambda. So the all the so why we see the blue sky is basically of this relic scattering. Because of the relic scattering, the atmospheric uh, the relic scattering happens from the atmospheric oxygen and nitrous molecule sizes, and because of that, you know that the all the violet light get scattered more, and the light is red. So basically, the light is as the threshold where it is not being scattered, like it is being scattered enough that we can see it, but it's not being scattered completely before coming to the our eye. So the intensity for relic scattering is proportional to lambda to the power minus 4. So lambda to 7 lights of the white light, 7 color. That has the shortest lambda 400 nanometer. This is 600 nanometer. So lambda r is 1.5 times of lambda v. So intensity varies at 1 to the power lambda by 4. So basically lambda 3 to the power 4 by lambda r to the power 4. So that is 1.5 to the power 4 lambda e to the power 4, e to the power 4. So lambda 1.5 to the power 4 is basically 5.0625. So intensity of, see that the 400 nanometer is about blue, because violet is completely being scattered. So intensity of blue is like 5 times intensity of red. If we give the actual wavelength value of violet and actual wavelength of red, we are taking the approximate value. So we can see that this is the scattering is 5 times less for red wavelength than the blue or violet wavelength. But if we put the value of violet and blue wavelength, you can see that, and it's evident by our eye that the blue wavelength is scattered enough that it doesn't escape before reaching to Earth. So the we can compare that the scattering of violet is how many times the scattering of the blue. So that's the comparison. Then another thing is, due to the red scattering, we see sunrise and sunset, the red color of the sun. We know the sun, from sun we get all the 7 colors, but why do we see it at a red? Because the length of the atmosphere traversed by the sun rays is maximum at sunrise and sunset. So when the distance is maximum, we can see that red light is being scattered much less than the blue light. So the only red light remains. All the other colors got scattered significantly. When at midday, the sun rays travel the least amount. So basically, we can have all the light, all the sun rays can come to the earth, and all the 7 colors is present there, and the sun appears whiter. And another thing, even if sky, we see the clouds which are white. So why we see the white clouds? Because the light particle being scattered by a much more large particle when it being scattered by those clouds. That's why it appears white. So they are not really scattering happening. Only me scattering is prevalent there. Inelastic scattering is Raman scattering. So what happened in Raman scattering? Basically, that a particle have many energy bands in itself. So if the particle comes from have like does the interaction and goes to an upper band and comes back to that band, that is elastic scattering. That it doesn't like energy and momentum got transferred to was conserved. It is elastic scattering. But what happened, that is a particle if is there and goes to the upper band and comes back to the not that band, or from this band it goes to the lower band. So there is energy difference. So here the photon, uh, in that case, it is gaining energy, and in this case, it is losing energy. So that is corresponding to Stokes and anti-Stokes line basically. Another in like inelastic scattering or Brillouin scattering, Compton scattering, incomplete scattering, the photon and electrons, such like they got interacts with each other. So that's on Compton scattering. We can get a Compton wavelength from that scattering. So this so this is the losing particle. So in the Stokes scattering, incident photons lose energy to the scatterers. So here the particle is gaining energy. So this particle is from the scatterer, but the incident photon is losing the energy. So this corresponds to Stokes line. And here the scatter particle are losing. Okay, sorry, it's not. Yeah, the scattering particle is losing the energy, but the incident photons gain energy. So this is anti-Stokes line. So between the Stokes and anti-Stokes line, Stokes scattering dominates. And using this Stokes and anti-Stokes line, we can write that these are the some characteristic features of some materials. So when human spectroscopy upon this significant Stokes and anti-Stokes lines, we do the Raman spectroscopy on the basis of this Stokes and anti-Stokes line, and we get to identify the material. So it is Raman scattering is one of the way to identify the material. So now I will discuss some question from the previous year. You can hear a person from the next room, but you cannot see the person. It's very easy. The option A is sound has longer wavelength than light. Sound penetrates wall. Lights bend around the corner. None of the above. So even if light went around the corner, you cannot see the person next room. That's not the option C. Sound penetrates wall, and it largely because sound has longer wavelength than the light. That is the reason that happened. Lunar sky is black, while the Earth sky is blue in color. Why? We know the answer is why. Because we see the color, because we have atmosphere. In atmosphere, we have nitrogen and oxygen molecule. That's why the scattering happens, relic scattering, and that's why we see the blue lights. But the moon doesn't have the atmosphere. That is why uh, there is no scattering, and because there is no scattering, we don't see any like uh, we don't see it. It's the wrong statement. The persons or some the machines who journey on the moon, they see black sky. So all are true. That moon has no atmosphere, and we see the blue light because Earth has atmosphere, and relic scattering is more for blue than the red. And so the option correct is D. All of the above. 3. Red color at sunrise and sunset in the sky is blue. 1. More may scattering, more relic scattering, less relic scattering, less me scattering. So here you can be confused by more and less, me and Lilic scattering. So basically they are asking a scenario where both the scattering is happening, and what do you think about, like, which scattering is, because of like which scattering has more influence on that phenomenon. So the red color, blue color, the color we see different color is because of relic scattering. So the answer is more relic scattering. Uh, because due to the Mie scattering, where the particle size are more than the wavelength size of the light, uh, we don't see the color different, like blue or red. We can see the like white portion of the light. Question number 4. What will be the ratio of the scattered intensity for blue and red light of same intensity, red light of same intensity when they get red. A relic and B Mie scattered. So when the lights are getting Mie scattered, they are, lambda blue is around 400 nanometer and lambda red is around 600 nanometer. So the options are 1 81 by 16, B 81 by 16 comma 1. Like this value is for this value is there for relic scattering, and the next value is for basically Mie scattering. So we know for relic scattering I is proportional to lambda to the power minus 4, and I have this calculation. So between the blue and red line, the scattering intensity is 5.0625 something. So this is the value 81 by 16. And for Mie scattering, the both like Mie scattering doesn't differentiate between blue and red. It's not wavelength dependent. So both light will be scattered at the same intensity. So the ratio is 1. So this is the answer basically. So B is the answer. I after rain, Q and then blue hue of sky becomes more intense because all the particles, like uh, wavelets, can wash off all the big particles. So that's why me scattering got less. That is why the blue hue of the sky became more intense. It is not due to like more of the relic scattering also, but it's generally due to the less of me scattering because the big particles is being removed by the water droplets of the rain. Scattering be due to no scattering due to less me scattering. So this is because of due to less me scattering. Why do clouds often appear right? The options are because they have water droplets, B, because they have more oxygen, than nitrogen molecules. That doesn't make sense because even if it has more oxygen than the nitrogen molecules, the oxygen and nitrogen molecule size is less than the wavelengths. So basically, we have option of me scattering and relic scattering, nothing in between. And oxygen and nitrogen molecules both causes relic scattering. So option B doesn't make any sense. C, because they have dust particles. Dust particles doesn't generally present in cloud. They have water vapor. Speaking, vapor is gaseous medium. It doesn't cause any scattering. So we see cloud because light being scattered by the cloud. Common sense or general sense says that yes, the clouds have water droplets and water droplets are big, so there are more chances of having of being present of water droplets in the cloud than the dust particles. So we see the clouds white because of mist scattering, and then mist scattering happens when the particle size is much bigger than the wavelength size. So water droplets and dust particles can do that, but the clouds, water droplet, the presence of water droplets is more prominent than the presence of dust particles. So this is the answer. Question 7. Which scattering is wavelength dependent? B. Me scattering. C. Raman. D. None of the above. So we know relic scattering is wavelength dependent, but also Raman scattering is wavelength dependent. Wavelength and also the particle dependent. So if you have studied Raman, you can say like that with different laser, like different laser of different wavelength. Using those, we can see different Raman peak. Like in one, with one laser, you can sometimes you cannot see the prominent peaks and of a sample, but if you change the laser wavelength, you might see that wavelength because it's basically coming going up and coming down of the particles in their vibration and energy levels. So Raman is also frequency dependent. So as it is frequency dependent, it's also wavelength. Here comes the next question. Which scattering gives the signature scatter? A. Relic. Signature is say a particular peak due to like that scatterer. So you can see that relic doesn't give that. Relic is wavelength dependent, but of the light that being scattered. It doesn't depend of the scatterer. If the size of the scatterer is way below, then the wavelength. Me, Raman, scattering, and D is both A and C. So the answer is Raman. The line in which kind of scattering green light can be scattered as the red light. So A is Stokes Raman, anti-Stokes Raman. So green light wavelength is less than the red light. So red light wavelength is more. So its energy is less. So basically, the photon is losing its energy. So it happens in Stokes Raman. Relic and D is mean scattering. So the answer would be Stokes Raman. So this is for today. I'll discuss more question like this in the next class, and I'll upload the video right away. But some of the slides I was discussing for first 30 minutes of this tutorial has gone missing. So I'll write those slides and then upload these slides. Thank you for coming. See you in next class.